Okay, so these are some classic formulas for the volume, right? So we'll prove them today. So the volume of a cylinder with a cross-sectional area A and height h is defined to be AH. Yeah, so if you have a cross-section, if you cut a cross-section and the cross-section has area A, then you just multiply by h, you get the volume for the whole thing. Yeah, you can think about it as pieces of coins. So it's basically cross-sectional. If you think about each of the coin area as, if the height of these coins is really small, then you're essentially multiplying by A times the height of the stack, all right? Now, the volume of a general solid is defined using calculus. So how do we define it? Again, so consider the following solid. So this is your solid S, and you want to find out the volume of this solid. So what you do is, you can, you can divide A to B into some intervals. And in each of the intervals, you're going to approximate it by a cylinder. Okay, so it will be like a cylinder of this form. Okay. Okay. So now, if you approximate this volume by 4 cylinders, this is how it looks like. If you approximate it by 10 cylinders, you see it's getting closer to the actual volume of the solid. And if you approximate a 15 cylinder, it gets closer. So the more number of cylinders you approximate it with, the better approximation for the volume you will get. In general, so this is the idea behind, this is a similar idea behind the Riemann sum. So what you do is you take your solid S for which you want to compute the volume. Suppose S lies above A and B. What you do is you divide A and B, A to B, the interval AB into, so divide AB into n equal parts of width. The width is then going to be delta x, which is B minus A over n. Now what you do is, over each width, you take any point. So if you take each of the subintervals, xi minus 1 to xi, you choose any point random in between xi minus 1 and xi. So you look at the cross-sectional area, which is this pink colored region, and then you draw a solid with that cross-section as the base and the height to be the width of this interval, which is delta x. So the area of the cross-section above xi star is A of xi star, and therefore the volume is going to be, so first what you do is you do AXI star times delta x to find volume of one of these, volume of this object above one interval. You add all of them up to get volume on top of each subintervals. And then what you do is you take the limit as n goes to infinity to make it refined. So this is the volume of the solid. Now this thing can be written in terms of integral as follows. So if you recall, this is a definite integral a to b ax dx. So this is how you find a volume of a object or solid. Okay. So now this definition can be refined in terms of integral. So again, let S be a solid that lies above A and B. as in this case. So you have solid S lies above A and B. Now the cross-sectional, if the cross-sectional area of S in the plane PX through X and perpendicular to X is AX. So the idea is you basically take a cross-sectional area perpendicular to X-axis. Then you get this cross-sectional area. Okay. And then what you do is you integrate it from A to B, AX dx, then you get the volume. So this is the definition of the volume. It came out of our intuition about how the volume should be. Okay. But this is the definition. Okay. So now let's embark on the following problem. Find the volume of a pyramid whose base is a square with side B and whose height is h. So we have already seen this above in our formula list. The volume turns out to be B square h by 3. Okay. So let's see whether our new method of computing it agrees with that. So what I'll do is, to make the cross-sectional area look nice, we'll move the solid in this way. So we'll turn it around and place it like that. Now we need to, on top of X, we need to find out what is the area of this cross-section. Okay. So now to do that, we need to find out what the area is, right? So consider the following. I'll draw on top of H, let's take this point and I'll draw so now if you look at these two triangles, so here H, we have H, and since the base is, the total base is B, this height is half of that, so this is going to be B by 2. So this part length is B by 2. This, the total X length is H, right? Because that's what is given here. So this total length is H. This distance here is X, and we need to find out this height here, right? Because then we can double it, and then since the cross-sectional area is a square, square of that doubled height would be the area of cross-section. So these triangles are similar. Why? Because this is 90 degree, this is 90 degree, they share a common angle. That means the sides will be in proportion. So if this is y, we get y divided by x equals to height of the bigger triangle, b by 2, divided by the base of this bigger triangle, which is h. Or this implies y equals to b by 2h times x. So now what is the cross-sectional area? So AX, the cross-sectional area above X is given by what? So double this Y, so 2y will give me the side, and then you need to square it. But it has to be written in terms of X, so we have 2 times b x by 2h, the whole square, which is same as b square h square times x square. So therefore the volume is given by 0 to h, because that's what your x is going from 0 to h. Then the area of cross section is b square by x square, sorry, b square by h square times x square dx. Now you can take out the constants. B and h are constants, so they come out. Integration 0 to h of x square dx. This is going to be b square x cubed by 3, 0 to h. And then when you put the h in, you get b square h cubed by h square times 3. The h and h will cancel, h and h square will cancel. So we get b square h by 3, which is what we expected. So let's ask the following question. So in this case, we were able to find out the cross-sectional area. So when can we find out the cross-sectional areas? So in one case, we can find it very easily. So those are what are called solid of revolution. So what is a solid of revolution? What you do is you take a region or an area in a plane and rotate it along a line. So suppose if I take this line, if I take this region and I rotate it along x-axis, what would I get? I'll get a cylinder, right? If I take this guy and rotate it around x-axis, what will I get? I'll get a cone. If I take this region and rotate it around x-axis, what will I get? A sphere, basically, right? What if I rotate this guy? So if I rotate this guy around x-axis, along x-axis, we will get a kind of a picture shape object. Yeah, I'm just drawing the contour line so that you can really see it's a three-dimensional object. So then the question is how to find out the solid volume of solid of revolution. Okay, so let's embark on this problem. So find the volume of the sphere with radius r by rotating a semicircle above the x-axis. So you have a semicircle. So make a cross section of the radius through one of the equator or through the largest circle. Now, in that case, you can let z equals to 0. So the sphere, which looks like x squared plus y squared plus z squared equals to r squared, we are now taking the upper circle and rotating this circle along the x-axis. So let's see how do we go about it. So in this case, when you put z equals to 0, you get this slice or this circle. Now you have x squared plus y squared equals to r squared, or you get y equals to plus or minus r squared minus x squared. Yeah. And we are taking what? Rotating the semicircle about the x-axis. So we'll take y equals to square root of r squared minus x squared. So we are going to take the upper part, which is what? Which is, so this is going to be minus r to r. So now we want to find a cross-sectional. Look at the cross-sectional. So cross-sectional area is also a circle. Now, what is the area of this circle? Let's take cross-sectional area above x. So area of x is going to be, now note that here, y gives the radius. And what is the y? Y is given by square root of r square minus x square. So is pi r square, right? And what do we get in that case? It's going to be pi square root of r square minus x square, the whole square. So this is the area of this cross section. Now you integrate it all from minus r to r to get the volume. So volume is going to be minus r to r pi square root of r minus r square minus x square, the whole square dx. This is going to be minus r to r pi r square minus x square dx, right? Now, what kind of function is this? So now we need to evaluate this integral. Now you can notice quickly that this function is an even function. So this integral is going to be 0 to r 2 times pi r square minus x square dx. Now let's integrate this. So the integral is going to be pi r square x minus x cubed by 3, 0 to r. Now when you put r, you get pi r cube minus r cube by 3. Now when you put, and then there's this 2 outside, right? So let's keep that 2 outside as well. And then when you put 0, the whole thing becomes 0. So we get what? 2, you multiply this, so you get 3. So 2 times pi times 3r cube minus r cube is 2r cube by 3. Now this is going to be 4 pi r cube by 3. Yeah, which is the volume formula you have been memorizing for such a long time. Yeah, so this is how you find the volume of this object. Now consider the following problem. Find the volume of the solid obtained by rotating the region bounded by the curves y equals to sine x, x equals to pi by 2, and y equals to 0. So y equals to 0 is your x-axis. So one of them is x-axis, so that's fine. What is the other region? The other region is x equals to pi by 2. So let's say x equals to, so pi by 2 is somewhere here. And then the other region is y equals to sine x. So what is the other one? Sine x. So the sine x looks like, if this is 1, at pi by 2, the sine x value is 1. So this is how the sine x will look like. Okay, so this is the region you are rotating. So the region here is what you're rotating, right? So let me shade this region. Yeah, so this is the region. You're rotating around what axis? Around x-axis. Okay, so now if you rotate this region, let's try to see how will the shape look like roughly. So I'll draw the shape. So the shape will roughly look like, so on top of x, if you draw, you will get a semicircle, right? So what you need to do is you need to basically find, you get a circle, yeah, and you need to find out radius of the circle. So on top of x, what is ax? Yeah, ax is this region here, right? So this is your ax. So let's find the area ax. So this is going to be pi, and this is given by y, and what is your y? Your y is given by sine x. So pi y square, so which is going to be pi sine x square, right? So your volume is given by, this point is 0, this point is pi by 2. So 0 to pi by 2, pi sine square x dx. Now you want to integrate this. So take pi out. 0 to pi by 2. Now there is no formula for sine square x. However, if we double the formula, double the angle, we can see that, so sine square x, when you double the angle, you get 1 minus cos 2x by 2. So this will become 1 minus cos 2x divided by 2 dx. Now you can integrate it. So take pi by 2 common. We have integration of 1 is x, integration of cos x is sine, so cos 2x is sine 2x divided by 2, 0 to pi by 2. Now when you put pi by 2, you get, when you put pi by 2, you get pi by 2 minus sine of 2 pi by 2 divided by 2 minus pi by 2, or we can put pi by 2 outside, so you get 0 minus sine 0 by 2. So all these are 0. So this is 0 because this is same as sine pi. This is 0, this is 0. So you're left with what? Pi squared by 4. So this is your answer. So such a method is called disk method, or later on we'll say there is a variation of this which is called washer method. So let's move on to the next part of the problem. So again, find the volume of the solid obtained by rotating region bounded by a curve y equals to square root of x, y equals to 1, and x equals to 0. So let's draw this. So y equals to square root of x, y equals to 1. So how does y equals to square root of x looks like? So y equals to square root of x goes like that. So this is y equals to square root of x. You have y equals to 1, which is a line. And then x equals to 0 is the y-axis. So you have this region which you want to rotate around what axis? Around y-axis. So let me shade the region. So this is the region we are looking for. Okay, and we are going to rotate it in y-axis. So the shape will look more or less like this. Okay, so now you are going to cut a cross section in y-axis. Okay, so a cross section in y-axis will look like this. So now, what is the area of this cross section? So again, first let's find the point of intersection. So y equals to square root x and y equals to 1. This implies, where do these curves intersect? When square root of x is 1, or this implies x equals to 1. So this point is 1, 1. Okay. Now we want to find out the area of the cross section. So in this case, the formula for y and x would be, so x and y would be interchanged. So in this case, what we'll have is, this is your circle, right? So now what is the area of that circle? Area of that circle is given by pi. What is your radius? The radius is basically x value. So pi x squared is your area, but it's dependent on y because you're cutting a cross section in terms of y. So the function also has to be written in terms of y. So you get pi instead of x. Well, what will I have? So my x is same as y square for this curve. So I will have y square the whole square. So in that case, the volume will be integral 0 to 1. Now we are looking for y 0 to 1. A of y dy, which is going to be 0 to 1 pi y to the power 4 dy, which is pi y to the 5 over 5, 0 to 1, and that is going to be pi by 5. Yeah, so the idea is in this, the axis you're rotating with along or doing the revolution along, you have to cut a cross section perpendicular to that axis. So you see here we rotated in the y-axis, so we have to draw the cross section which is perpendicular to y-axis. Okay. So let's move on to the next problem. So find the volume of the solid obtained by rotating region R, which is enclosed by curve y equals to x cubed in the first quadrant and about the line y equals to 3. So let's first do y equals to 3. So y equals to 3. So y equals to 3 is this line. So you're going to cut a cross section. So you are looking at a cross sectional area because you're rotating it parallel to x-axis. So this is how the area of the cross section will look like. Area of cross section is combination of two circles. One is the outer circle and the other one is the inner circle. So now the area above on top of x is this annulus or disk. Now if you look at this disk, this is how it's going to look like. So you have an outer circle and then inside you have what? An inner circle. All right. So now what is the area of this disk? It's basically, if you look at R outer and if you look at R inner, so just let this be R inner, then the area is going to be, this area is going to be pi of R outer square. That is the outermost circle, and out of that you have to remove pi R inner square. So in this case, let's see. So what is the radius of the outer circle? So the outer circle radius is all the way from here to here, right? So from here to here. So this is my R outer circle, okay? So okay. And now what about my inner circle? My inner circle is basically from here to here. Okay. So now note that the total length is, this total length is 3. So what is R outer? So R outer is going to be this total length 3 minus this height, right? So it is minus this part. And this part is given by what? Y equals to x cubed. So R outer is going to be pi. So the total length is 3 minus x cube. So this is your R outer. Now what about R inner or the inner radius? So there's no pi in the, so the total length 3 minus the x squared. So this is going to be, again, the total length is 3 minus this much, which is given by y equals to x. So we have 3 minus x. So therefore, your a of x is pi r outer square minus pi r inner square. And what will be the volume? The volume is going to be 0 to, where do they intersect? They intersect, here is 0, x is 0, and here x is what? 1. They intersect from 0 at 0 and 1, so it's going to be 0 to 1 pi of 3 minus x cubed, the whole square, because our outer square, minus pi of 3 minus x square dx. And you can find out this volume by expanding it out. Now let's do the same problem with x equals to 2. So let's embark on that. Again, the region we are interested in is basically taking this region R and rotating it around. So this is your region which you're going to rotate around what? Around x equals to 2, which is this line here. So when you rotate, you will get a shape of the following form. So you will look at the cross-sectional area on around x. So if you, so this is how it will look like. So this is your R outer. So in this case, you have R outer. So again, you will have A of y, right? Because you're looking at the cross-sectional area perpendicular to y-axis. So notice that R outer in this case is going to be this total length. Now, what is this total length? Again, we'll employ the same technique. This total width is 2. And out of this width, we are removing, so R outer will be for the bigger radius, R naught. Out of this, you are removing this much. Yeah, this much part you're subtracting, which is given by the x value of the line, but in terms of y. What is the x value of line in terms of y? It's basically y. So it's going to be 2, the whole thing, this whole thing, minus the x value here, with given in terms of y. So we have R outer is 2 minus x. Now what about R inner? The inner radius is going to be, again, the whole thing, which is 2, and out of that you're subtracting this part from here. So you're subtracting this part. Yeah, and to subtract that much part, basically again is what? The whole thing is 2. Out of that you're subtracting the x value of the curve y equals to x cubed, but written in terms of y. So this implies x equals to cube root of y, and this is going to be 2 minus cube root of x. Sorry, cube root of, nobody corrected me, it has to be written in terms of y. So 2 minus y here and 2 minus cube root of y. So therefore, what do we get? We get volume is going to be 0 to 1 a of y dy, which is going to be 0 to 1. A of y is what? Pi r outer square, which is 2 minus y the whole square, minus pi r inner square, which is 2 minus cube root of y the whole square. dy. So why this for washer method? Because if you look at this cross-sectional area here, in this case, this cross-sectional area looks like a washer. Whereas if you look at this area here, the cross-sectional area, it looks like a disk. So what is a disk? It's a circle, but things are filled inside.